introduce Yash Deshpande. He's RAM Fellow at the Math Department at MIT and MSR Research in England. He has done very interesting work in message passing algorithms and price probability.
Thank you, Hari. I must thank and Devasad for inviting me to this workshop. Despite the fact that I lived here for 4 years during undergrad, I didn't ever come to the IFR. Now I feel quite happy that I'm able to remedy this error. And this is of course thanks to them. And also I'll thank you everyone for valiantly sticking to the towards the end of the workshop. So I promised. So this is why I decided not to use it, because thankfully this talk is amenable to a blackboard, and hopefully we will keep it a little bit conducive to the time of the day. Okay, so let me finish writing the title. So I'm going to be talking about estimating low rank matrices noise, and so let's do. From Pingla theory. So the general setup that I'll put a formal model about in a few minutes, but the general setup that I'm going to be talking about will be problems of the following kind. So you observe a matrix A. Think of this as a large symmetric matrix of the form lambda times L plus W. Okay, where so this is your observation. The matrix L is what you wanted to estimate. So L is a matrix that is sort of hidden, which you want to estimate, and we'll assume that this is low rank, and I'll tell you in the example how this works. For simplicity, I will factor out the strength of the observation in terms of scalar signal to noise ratio lambda. So this will be parameter which is, by the way, is my handwriting legible to everyone? So should I write larger? Okay. Yeah, perhaps I should ask people at the end of the hall. And then W is going to be, some sort of noise model. Okay, so you're given, A, which is putatively of the form, there is some signal which is characterized in its strength by lambda and its structure by L, which is hidden in noise. You want to estimate A. Okay, so now you have all been through this workshop. If you ask Greg, then he will say, you should do the estimate, right? So it's natural that the signal that you want to estimate is low rank. So if you ask Greg or Devavrat, and even I like to be in company, so I will also put myself there. But it's completely natural that why should you not do it? You can estimate L by doing something like taking A, finding its all of its eigenvalues or singular values, and truncating to the large. Okay, so what I want to do today, so this is a perfectly legitimate thing to do, and in many applications this is very good. But what I want to do today is to try and give a couple of examples where somehow you can go beyond what you do with these tools, and mostly the results which I've explained use techniques from implicit signal. Wrong button. Good question. Actually, it turns out that so I will assume some normalization on L in the formal model that will become clear. So I will assume, for instance, that L has nuclear norm 1. Yeah, you can always, of course, rescale everything by dividing by lambda, and then that becomes the standard deviation. But yeah, so for convenience, I will assume some sort of normalization where L, has about some standard size with respect to W, and then the SNR is parameterized. Actually, lambda squared, but no. So think of A as a large random matrix, and one example is coming right. So think of A as a large symmetric. Okay, so still getting used to the board. Okay, so what is the model? So the model that I will talk about is called, so in statistics, I think, or this came about in sociology literature in the 80s. It's called stochastic block model. And computer science, so called the slanted partition. Okay, so here the idea is that you observe a graph. G. You observe it, meaning you know its adjacency. So its adjacency matrix is A. Okay, so in this case, this A is the same as that A, so I'm going to think of A as the adjacency matrix of this graph. And the graph is generated putatively as follows. So every node comes with a color or a category. So nodes of G have labels. Say for simplicity throughout today, I will talk about labels plus minus 1, and I will put in this in a vector v0 all of the labels G, all of the labels of the nodes in G. So now this becomes a vector in plus minus 1 to the n. Okay, now conditional on these labels, the graph G is a random graph generated, and the distribution of this random graph, so the probability that the nodes I and J are connected, conditional on V0, this is going to be some constant C in on n if V0 is V0J, and C out on n. Okay, so the way to think about this is so the way to think about this is that there is a graph. Okay, and then some of the labels have some of them have labels plus, some of them have labels minus. Okay, and now you put an edge between every node of the graph with a prescribed probability, but the probability depends on whether the nodes have the same label or a different label. So if they have the same label, you're going to put an edge with probability C in over n. N is the size of the graph, and otherwise, so this edge, for instance, might exist with probability C in over n, and the other edge, say something like this, might exist with probability C out. Okay. So this is called the stochastic block model. I'll also assume that you have roughly balanced state. Think of V0 as being uniform on the type of cube. Okay. Right. Yeah. So yeah. Otherwise, the edges. A is the adjacency matrix of the graph G. So it's basically going to be 0 if I put an edge. Sorry, 1 if I put an edge, and 0. Sorry. V0 is a vector, each entry of which corresponds to a vertex of the graph. Right. 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 So there's since we're not in the United States, let's talk about US politics. So there are roughly two types of people in the United States: one whom are Republicans and one are Democrats, the Republicans are labeled as plus, Democrats are labeled as minus. There's roughly equal number of. There is no normative meaning to anything that I'm saying. Okay. So throughout I will also so I have to put the parameterization lambda. So it's convenient to think that throughout I will think of Tn as being d plus lambda square root of d, and C out lambda square root of d, for d being some fixed number and lambda being fixed. So if you look at this, what this means, so imagine that if Cn were equal to C out, then clearly the graph edges appear with the same probability irrespective of what the community is on the edges, right? So it's just a random graph. So the graph contains no information about the pluses minus labels if Cn is equal to C out. So the difference clearly shows somehow if the difference is large, then this shows something. If the difference is small, this doesn't. So the difference I'm characterizing by lambda, and for technical reasons I will rescale it by square. The adjacency matrix A will be given to us. We will not know V0. Yeah, so we want to estimate V. We want to estimate the label V. Okay, so that's yeah. So I will make all possible bad assumptions. So I will assume that V is known. V is actually not hard to estimate, so that's not a terrible assumption. I will assume that lambda is known, and there will be some other parameters coming up. I will also assume everything there. So I will make all the worst assumptions. Excellent question. It turns out not to matter, and I'll explain why. So hold on to that thought. But maybe about 10, 15 minutes in, you can ask me the question again. Yeah. Anything else? Yeah. Think of D is so D is just the expected average degree of a vertex. Unconditional. Mm-hmm. Mm-hmm. Right. And that's a good question. So I'll explain how this fits into that. Okay. So so that's actually a very simple calculation. Okay, so what is the task? Okay, so I'll talk about a few different questions. So the task is estimate V0 from A, and also in the latter half, perhaps I'll talk about also what happens if you have additional side information, which is of an interesting nature. So the natural questions. So one, which is the for what SNR lambda is this possible? Is this okay? So another version of this question is actually what is the best estimation error? And then the third, sort of other question is how do the answers to these questions change if you have side information, which I'll come into. So to answer Sanjay's question, perhaps we should do first calculation. following. So the first calculation is, okay, what does this have to do with whatever I said before? So if you separate A into its expectation plus the deviation, okay, so this is what I would call the signal. And then if you do a little calculation based on whatever this is written here, you see that this is D times 1 transpose over N plus lambda square root of D times D0 transpose over N plus things that I will call noise. Plus this stuff is just random. 0 means random. Okay, so the signal part, the expectation of A given these, so splits into a sum of two rank 1 matrices. The first one contains no information. The first one contains no information about the communities. It's just sort of how dense the graph is. The second one is really what we want to get at, and then whatever else is left, the stuff here is yes. So the number of communities is yeah. So the rank here is like number. You can rescale it, get rid of this one. Any other question? Okay. So, I'm sorry. Perhaps I don't know. What does it? So perhaps I don't understand. What is specific mean? Mm-hmm. Yes. A has n squared numbers. The ones that I want to estimate are only the pluses and minuses in B0. There's only n numbers, or n bits that I want. Right. Yeah. So everything is normalized. Makes sense. Sense that if um, if this noise is well behaved, then the spectral norm of the noise is here. Then you would expect it to behave as the spectral norm of the signal. So in that sense, things are well. For instance, if you forget this part contains no information. But if I compute the spectral norm of this matrix, this is the order. Okay. And in this case, at least for large D, or D diverging slightly with n, the noise behaves. I'm sorry? Yeah, so that's why lambda is there in R, because without the lambda, these. I'm sorry? Yeah, so that's why the lambda is exactly the same. Because okay, D is about whatever number it is. D0 has plus minus 1, so this object always has spectral norm. So there is, so I've absorbed into this part, whatever signal noise there is, and for other. Okay, excellent. So I will call this model. So there is. I'll call this model SPM for short. Okay, so what is known about this? So in the past, I think 7 or 8 years, there has been a lot of work on this model. Okay, so okay. So I didn't completely tell you how what we mean by estimate. So there are two metrics that are essentially equivalent, but that make sense in this case. So the first is called the overlap. If I'm given a guess v hat of v0, I'll call the overlap v hat. I'll define this as basically the scalar product, the inner product between v hat and v0. Take the value, and then you normalize by WL2 norms of v hat. Okay. And then the other is the mean squared error. Mean squared error of v hat. So this is going to be slightly different from what you might expect. It's going to be the mean squared error of its outer product with itself minus the outer product of v0 with itself. Okay, and I normalize by. So why am I? Okay, so these two metrics are roughly equivalent. So it's not very hard to prove that they are. But why am I doing this? So why am I doing for instance, the absolute value here and taking the outer product here? Well, simply because if I look in the model, if I change the v0 to minus v0, then the distribution on A remains. So if I see over there, if I change v0 to minus of itself, I don't see any difference. This means that the distribution is invariant sign. I must remove this invariance. How? For instance, this thing is invariant. So up to a global phase shift. Okay, so what is known about this? So there is a very nice set of results theorem. This is due to Mosel, Niemann, Fly, 2012, the same set of authors, 2015, and simultaneously by Soulier year. So what they proved is that non-trivial estimation of V0 from A possible if and only if lambda is bigger than 1. Okay, so what I mean by non-trivial estimation, so this means, for instance, the expected value. So there exists an estimator so that the expected value of the overlap as the so that in expectation this quantity is positive. So for instance, if I took v hat and completely ignored the data and I just tossed a coin. Okay, so maybe I've decided to be entirely lazy and ignored the graph that I saw. I tossed coins. These coins, random coins, are independent of the data. This will give me completely random guesses. In that case, this limited. Not if I guess essentially if I guess completely randomly, then I'm not any signal. On the other hand, if for instance, if d0 is a plus minus 1. So v hat is all zeros. Your question still stands. V hat is all zeros. Yeah. Yeah. So I mean, okay. So if, I'm assuming that you are going to return an estimate that's trivial. Sorry. Yeah, that's not. So you can define it however you want. Or for instance, I can force you to return an estimator that lives on the. Okay, so in this theorem, you just need d bigger than 1. So for any d bigger than 1, for any d bigger equal to 1, then this is. Okay, so as in whether it is bigger than 0 as a function of lambda. Okay, so Ali is already 2 boards ahead of me. So that's coming. So that's question 2. I'll tell you about it. Excellent question. So in the case that D, I mean this one, it will only make sense when this allows. I'm sorry. Yeah, there is a region in the large. Yeah, so okay, think of D as being a large number. Think of D as being 50 or whatever it is. So if you somehow you the place where you care about. Sure. Okay, so maybe I'll state the next theorem and then it will become clear why I parameterize. This is not the standard parameterization, but hopefully this should make it clear. Or okay, so the first result I talk about very quickly. Bring this down. Yes, first result I'll talk about very quickly. Talks about what is the best possible estimation error, and sort of exactly answers Ali's question. So